In a deadlock, processes never finish executing, and the system resources are tied up, preventing other jobs from starting. Before we discuss the various methods for dealing with the deadlock problem, we look more closely at features that characterize deadlocks. First, necessary conditions. A deadlock situation can arise if the following four conditions hold simultaneously in a system. Mutual exclusion. At least one resource must be held in a non-shareable mode. That is, only one process at a time can use the resource. If another process requests the resource, the requesting process must be delayed until the resource has been released. Such as printer is mutual exclusion resources, but the CPU time and the memory, physical main memory, are not mutual exclusive resources. Okay? And hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. Third, no preemption. Resources cannot be preempted. That is, a resource can be released only voluntarily by the process holding it, after that process has completed its task. Fourth condition, circular wait. There exists a set of waiting processes. That P0 is waiting for a resource held by P1. P1 is waiting for a resource held by P2. And Pn-1 is waiting for a resource held by Pn. And Pn is waiting for a resource held by P0. We emphasize that all four conditions must hold for a deadlock to occur. The circular wait condition implies the hold and wait condition, so the four conditions are not completely independent. Second, Resource-Allocation Graph. Deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. This graph consists of a set of vertices and a set of edges. The set of vertices V is partitioned in two types of nodes, P1, P2, Pn, the set consisting all the processes in the system, and R, that the set consisting of all resource types in the system. So here you look at this resource allocation graph. The regular box represent resources and the circular represented processes. Okay, so a directed edge from process Pi to resource type Rj is denoted by Pi to Rj. It signifies that process Pi has requested an instance of resource type Rj and is currently waiting for the resource. A directed edge from resource type Rj to process Pi, it signifies that an instance of resource type Rj has been allocated to process Pi. A directed edge Pi to Rj is called a request edge. A direct edge Ri to Pi, Rj to Pi is called an assignment edge. So look at this picture. That means resource R1 is allocated to P2 one instance, and process P2 is requiring one instance of R7 of resource R3 Okay. We represent each process Pi as a circle, and each resource type Rj as a rectangle. Since resource type Rj may have more than one instance, we represent each such instance as a dot. Okay, so here, for resource R2, there are 2 instances. For resource R4, there are 3 instances. Given the definition of a resource allocation graph, it can be shown that if the graph contains no circles, then no process in the system is deadlocked. If the graph does contain a circle, then a deadlock may exist. If only one instance per resource type, then deadlock. If several instances per resource type, possibly of deadlock. So let's look at this. This one, though there is a circle. There is a circle, and there is also a circle here. But because resource R1 and R2 both has 2 instances, so no deadlock. But here there is a circle, but there is a deadlock here, deadlocked. You can see that. Okay.